Hi, everybody. I'm Angelo Ricarte. I'm a scientist at the Smithsonian Astrophysical Observatory, and I'm one of the AGN demographics leads for BHEX. And I'm coming to, I've come to the EHT and BHEX from the perspective of black hole galaxy coevolution, where for a lot of people, those who model galaxies, the black holes are only exciting insofar as what they do to the star formation rates in their host galaxies. It's been known for a couple of decades that while supernova feedback is able to curtail the overproduction of stars in Milky Way mass galaxies and lower, when you go to higher galaxy masses like M87, there was some missing ingredient that was needed in order to prevent the overcooling of gas and production of stars. And we now know that this is AGN feedback. Basically, everybody accepts that this is a crucial ingredient for building an accurate galaxy at high masses. This is an early but illustrative example that I'm showing you here from Di Matteo et al. 2005. Nowadays, AGN feedback is not usually this explosive, but this gets the general picture across, where we have these two colliding disk galaxies, and when an AGN turns on, it heats up and blows away a lot of this gas, turning what were initially disk galaxies into something more like an elliptical. Now, although a couple of decades have passed, what we call subgrid physics, that has to do with how you model the black hole accretion and feedback, remain some of the most uncertain aspects of these kinds of simulations. And I wanted to be concrete and show a couple of my favorite cosmological simulations, many people's favorite cosmological simulations, and give you an idea of what is state of the art right now. These are applicable for a wide variety of applications, but well, when you're simulating a giant chunk of the observable universe, one has limitations in resolution and have to make some approximations. So in the case of asteroid, for example, the black hole accretion rate is given by the Bondi accretion rate times 100, where this is a dimensionless fudge parameter that they say to correct for unresolved ISM. Really, if you just don't include this, they don't grow black holes at all to reproduce what we see. And in the case of illustrious TNG, they have this model for feedback, a thermal mode from radiation and a kinetic mode from jets. And there's a transition here which has this awkward mass dependence that we don't expect to come out of, say, GRMHD. But they need this in order to quench galaxies, that is, reduce their star formation rates efficiently, suggesting that there's some sort of missing physics on some scale that needs to be better understood. The reason for these shortcuts is the resolution that we see on the bottom, roughly on the order of a kiloparsec, whereas the standard GRMHD simulations, if you believe them out to say 100 M or so, would get to perhaps 0.03 parsecs if we do 100 M for M87. And so this is where the EHT and BHEX and our demographic sources can provide an anchor for our understanding of black hole accretion and feedback that we can use to inform these evolutionary models that people can use for galaxies. And I've been especially excited about the ability for BHEX to give us the resolution to get EHT-like images for a much larger sample of objects. This is a plot of Eddington ratio and mass for some of our favorite BHEX demographic sources, where we've whimsically scaled the size of each of these points to their angular size on the sky. And you can see that while M87 is big enough for the EHT to resolve, you certainly need to go out into space to access most of these, and perhaps super resolution may need to be invoked for some of these. Now, looking at it this way, I think it undersells the literal galaxies of information that we have that actually distinguish each of these as a unique laboratory for astrophysics. And they're all unique in different ways, and we can use these for comparative studies to study the accretion flow as a function of accretion rate, black hole mass, but also stellar mass, environment, and other aspects of black hole galaxy coevolution. As an example, we have NGC 4261, which lives in what's called a cool core, which is often described as inefficient or failed AGN feedback, and yet we see these jets. There's a weaker jet relative to M87 and M89 as well. M84 has a resolved Bondi radius where we can do, again, these kinds of comparative studies between Bondi accretion rates and whatever one infers from resolved imaging. And we can start asking other questions like, do we always get ordered polarization that we may use to infer strong and ordered magnetic fields? And one thing we certainly get for free is what may non-face-on black hole look like on horizon scales, since it seems nature gave us both M87 and Sagittarius star relatively face-on. And a more edge-on inclination perhaps will be more sensitive to otherwise invisible electrons in the disk that may be doing some kind of asymmetric Faraday rotation and depolarization on the image, for example. So what I've been doing is a lot of this modeling to give us a sense of the types of GRMHD that fit M87 and Sagittarius star, and using those types of models to inform our accretion and feedback. For example, in a paper a couple of years ago now, by me, Ramesh, and Brandon Kurd, we looked into MAD, magnetically arrested disk, or strongly magnetized simulations, and studied the feedback power and the resultant equilibrium spin, splitting it up into 3 different kind of modes of accretion: hot accretion, appropriate for things like M87 and Sagittarius star, a thin disk in between, and then super Eddington, where a geometrically thick disk can start to confine a more powerful jet again. We can take these recipes from GRMHD and then place them into semi-analytic models. So what I did in the paper this past year was put this into a semi-analytic model that I've developed called Serotina, where we initialize black hole seeds with spin 0 at redshift of 20 to 15. And what you're looking at here is the evolution on the M sigma relation, one of these that Chung Pei mentioned earlier today. As these things evolve through cosmic time and decrete, they're going to gain angular momentum from their accretion disks, lose it from the jet, and get scrambled by black hole mergers as well. So the new aspect here is to take into account these recipes from GRMHD that have modifications to spin evolution from the magnetic field. As an example, let's look at the most massive black hole in a 10 to the 14 solar mass halo that I ran. We're looking at mass, spin, and accretion rate as a function of time. So first, I'm going to look at a sane one, where by sane, I'm meaning the sanest possible sane, where the magnetic field has no effect on the disk dynamics. Under these very simple assumptions, it's not that interesting. You spin up to 0.998, and you stay there. If you account for black hole mergers, which we normally do in Serotina, this will cause some jumps. There are numerical relativity formulae that we can use to give you the resultant spin of the black hole. And then ultimately, there's a more moderate value at late times that it settles on. But if you take into account the magnetic fields, you can see now that the spins are moderated. And in fact, this is mostly due to the Blanford-Znayak mechanism. What you should see here is this gap here now between 1 and around 0.8 or so, which tended to be the equilibrium spin at an Eddington ratio of 1, where the black hole will be accreting and changing mass efficiently. So what we explored in this paper was implications in spin distributions that might be accessible to different types of observations. One that you heard about last night, if you were here, was is X-ray reflection spectroscopy, where here I've selected in Serotina for objects that have high Eddington ratios, and we're looking at a variety of different models here. Some things to take away is that, well, first of all, the observations are these histograms in the back, black or red for a D-biased version. And compared to the same simulation, which puts things more in the spin 1 bin, there's a bit more spread in the MAD model. And if you move the transition between hot accretion flow and a thin disk that can scoot around as well. On the bottom, we're looking at spin versus mass. And there are actually about 50 objects making up the distribution in the back that are the black histograms. But my statistics here are not great, and part of the reason is that I selected for the rare high accretors. If you look at the population as a whole, which I'm now going to add as these circles, they fill out much more, and you'll now see that some of these points are blue instead of red. In my encoding, that means that they're actually retrograde. And it turns out that the act of accreting is turning what would normally be retrograde, or what started off as retrograde objects in the simulations, into prograde systems once they start accreting efficiently and becoming an object that you might select from X-ray reflection techniques, meaning that this is an astrophysical selection effect. And so if you want a more representative sample of black holes, where most of the supermassive black holes in the universe are at lower Eddington ratio than what you can observe with X-ray reflection spectroscopy, that's where something like EHT and BHEX can jump in. This is a sample where I've now selected for things above 10 to the 8 solar masses and lower accretion rates below, in this case, 3 times 10 to the minus 4. And the point is that there's now more stuff on this side, on the retrograde side. And you can distinguish different assembly histories if one is able to constrain a spin distribution like this. And we've heard several talks the past couple of days telling us indirect ways in which we may be able to do this. And certainly we'll be able to for M87 and Sagittarius star from the photon ring. But even if you can't get a full distribution, any definitive retrograde would be interesting, as well as any definitive spin zero measurement, I think, especially for an object for which we see a jet. So wrapping up here, BHEX will be able to help us anchor models of accretion and feedback, allowing us to test our preference for strong magnetic fields that we have for M87 and Sagittarius star, with a comparative sample and see if there are any differences in different environments. Then we can use GRMHD models that represent the data to develop new recipes. I've shown that if strong magnetic fields are ubiquitous, the BZ mechanism can moderate spins at both very high and very low accretion rates. And this can be tested against jet powers and spin measurements from other missions to achieve a concordance picture. Thanks, and I'll take questions.
Thank you, Angelo. That was great. Do we have questions for Angelo? Angelo, do you have a sense of how many, if in the demographic business, what we really want, or what not we want that tens of thousands of sources, I'm sure, but what would be what you would like to be able to distinguish between the models?
Well, I don't know. I think more is always better. But at the very least, of course, you want you know, at least 2 that are on either side of some dichotomy, for example.
5.
So yeah, so it depends on how many dimensions you want.
A small but odd number.
Yeah. So we can, you know, they're interesting enough. There's an interesting enough range, I think, in mass and accretion rate here. I mentioned some of the different galaxy morphologies. We have radio loud and radio quiet, a cool core in there, edge on versus face on. The more objects you have, the more dimensions you can start doing comparative studies. I think that with 10-ish, we're able to make a compelling case for many of these. Because they're, yeah.
Andrew.
Yeah, hi Angelo, great talk. I have basically the same question you just asked, I think, just back at you. So since all these sources for the Bexonographics case are higher Eddington ratios than even M87, which we know is a few percent rate efficiency. Do you worry that our current models aren't capturing rate of feedback? And do you think that will help change the global structure or just the details of the images?
Yeah, I mean, I don't have more intuition than you or Charles, which is why I asked him earlier. Yeah, but I think this is one of the obvious things that we ought to be prioritizing in terms of simulation. We can pick several of our favorite objects and see what changes.